Hi, everyone. For today's lecture, we're going to look over the derivation of the work-energy theorem and then use that in a couple problems in order to solve for some of the things that we've been solving for: work, force, distance, and these types of problems. So what is the work-energy theorem? So basically what this theorem says is that work can be related to a change in kinetic energy. And so what we're going to do is we're going to go ahead and derive this. We're going to start with a few of the equations that should look familiar to us that we've done in the past. The first one of these is this from kinematics: v final squared equals v initial squared plus 2a delta x. That should be a this should be squared here. This is our distance, our displacement delta x, right? So we learned that a long time ago. We have Newton's second law, which is going to show up a lot, F equals ma. And then finally, we have our new equation that we derived earlier in this unit: work equals force times distance cosine of theta, and that we practiced using. So now we're going to take this equation and we're going to see that this displacement variable in kinematics is the same displacement variable that we have here. And so these two delta x's we're going to see what happens if we solve for this delta x and plug it into this equation over here. Also, in F equals ma, the equation a here, this acceleration is the same as this acceleration here. So we have two little pieces of information that we're going to actually use in here. The force here is related to the force here. So these three equations are interconnected in a couple of different ways. So we're going to look at that. All right, so the first thing we're going to do is we're going to solve equation 1 for d. And what that looks like is I'm going to first subtract over v initial squared to the other side and set that equal to 2a times d, or delta x. And then what I'm going to do is I'm going to solve for this variable d by dividing by 2a. So I can say that d equals v final squared minus v initial squared divided by 2a. All right, now what I'm going to do is I'm going to take this expression for d and equation 2, and I'm going to plug these both in for d and for f in this part of the equation here. All right. So my original equation is that work equals, rewrite that, work equals force times the displacement or distance cosine theta, the angle between the vectors. All right, if I know that that force equals mass times acceleration, and the distance is v final squared minus v initial squared divided by 2a, something pretty interesting happens. We have this acceleration variable cancel out. The acceleration from the f equals ma and then the acceleration from the d, they're going to cancel out, which is going to leave us with this really nice factor of 1/2 here, and mass, which we can factor out. 1/2 mass, and then I have a v final squared and a v initial squared. Now this cosine theta piece that we have, what we're going to essentially do is we are going to assume that the force and the distance in this part are working in the same direction. So we're going to assume, we're going to make an assumption here that theta, oh, that is not a theta, that's an asterisk. We're going to assume that theta equals 0 degrees. This just simplifies the math, so we can actually get rid of this term, and we can say that that's just 1. That's just a factor of 1, it goes away. So I get a 1/2 from here, the m from here, and I still have this v final squared minus v initial squared. And what I'm going to do is I'm just going to distribute this through and write this in one final way, and this is going to be our equation that we use, which is that work equals 1/2 mv final squared minus 1/2 mv initial squared. And this is the work-kinetic energy theorem. And the reason it's the work-kinetic energy theorem, and if you remember from that POGL that you guys did last week, we introduced this idea of kinetic energy. So kinetic energy, I'm going to skip around here a little bit. Kinetic energy, the definition is, energy an object has when it's moving. So when things are moving, they have kinetic energy. When things are at rest, they don't have kinetic energy. All like inherent particles are always vibrating, so there's always this vibrational kinetic energy that's happening, like within the molecules of a particle. So nothing ever really has zero energy if we look at it like the microscopic level. But we're talking about things macroscopically. Things are generally at rest. Like if you look outside and you see your car, it's not moving around. I mean, we could look at the individual particles in the metal, and we could see vibrational energy there. But as far as like visible kinetic energy, we would say that the car's at rest, right? So it would have no kinetic energy. So we're talking on a macro scale, not a micro scale. So this kinetic energy equation we learned from the POGL is going to be defined as 1/2 mv squared. This is the kinetic energy at a given point in time with a given velocity. So what I want you guys to see is if we look back at our derivation here, I think my picture is in the way a little bit. I'm good. Okay. So if you look at this piece right here, this kinetic energy definition right here, and we compare it, we can see it actually repeats itself twice in this equation, once with V final and once with V initial. And so this is really interesting because this essentially, this piece right here, we could define as kinetic energy final, and this piece here we could define as kinetic energy initial, which means that work is equal to final minus initial kinetic energy. And another term we always use for kinetic energy, or sorry, for final minus initial is the change, delta KE. So we can actually define work. The work kinetic energy theorem is that work equals the change in kinetic energy, and thus why it's called the work energy theorem. All right, so work, the amount of work that something does, is actually just defined by the amount of change in motion or change in kinetic energy that it gives an object. So when we're talking about forces, in order for a force to move an object, right, it adds an acceleration to it. That acceleration causes the velocity to change, to increase, and therefore it has now kinetic energy. All right, and that's all this definition is right here. All right. So pretty straightforward. We can write this a couple different ways. We can say work equals change in kinetic energy. We can say work equals KE final minus KE initial, or we can say that work equals, we can even expand this out further, 1/2 mv final squared minus 1/2 mv initial squared. So all these things are equal to each other here. And all of these are implicated within the work kinetic energy theorem. So when I say use the work kinetic energy theorem to solve a problem, I might just be looking at this first part, work equals changing kinetic energy, and maybe they give me my initial and final kinetic energy, but maybe they don't. Maybe they give me my final and initial velocity and a mass, and I need to figure out what those two are. Or maybe they give me the amount of work done, and I need to solve for V final or V initial. So we can use this equation in a lot of different ways. Right? So let's look at some applications here in terms of some problems. So I'm going to go to the next page here, and I got 4 examples we're going to work through, and that'll wrap up the lesson for today. All right. Feel free, again, if you want to try these on your own beforehand, or maybe watch one and then try one and then see what you can do. Feel free to pause the video, see if you could figure out, read the problem on your own and figure out what each part is. That might help you, grasp this a little bit more. But I'm going to go through all of them in detail. So, yeah, find the kinetic energy of a 50 kilogram cheetah moving at 30 meters per second. So we've got our little cheetah This is gonna be real bad. Let's draw this guy. Nice little tail here, a little cat paw. Another little cat paw. I don't know what cats look like. Not like this though. I don't know. I don't know, guys. This is we got some spots though. I know that. All right, let's add some spots. Wait, is that a leopard? Yeah, cheetahs have spots. I'm not crazy. Look at that. Look at them spots. All right. Now we go back down. Let's get a little yellow up in here. Maybe this right here. Let's color him in a little bit. Oh yeah, that's a nice cheetah right there. Oh gosh, I'm having too much fun. Physics is too much fun, guys. Now OneNote wants to keep my pen stuck on yellow. Not ideal. All right. So there's our sad little cheetah. We'll give him his ears and eyes back. Oh gosh, it's so bad. All right. Anyway, he's missing a leg too. We'll give him that last leg so he can run fast. Okay. Find the kinetic energy of the 50 kilogram cheetah moving at 30 meters per second. So in this case, we might look at this equation up here and say, okay, how does this apply? It doesn't, right? This tells us work equals change in kinetic energy, but this just asks for kinetic energy. So we're starting basic. We're starting at this kinetic energy equation right here. This is what I want. That's what I want to use right here. All right. So kinetic energy of the cheetah at moving at 30 meters per second is 1/2 times 50 times 30 squared. Let's just look at the units here. So we have this is in kilograms and this is in meters per second. So if I do the math out, 1/2 times 50 is 25. 30 squared is 90. Multiply those together and we get kinetic energy of 22,500 joules. Now, how did I get this unit? Oops. How did I get this unit of joules? The meters per second gets squared, if you recall that. So this is kilograms meters squared per second squared, which is a mass times acceleration times mass times an acceleration times a distance, which in our case is our force times the distance, which is work. So units of joules. Now, this is a derived unit, but the units do work out. You can think of it in terms of kilograms times meters per second squared times meters. This is our mass, our acceleration, and our distance, which is F equals ma. So this is a force, these two units, and that's a distance, and FD was our equation for work, which gave us units of joules. All right. So energy is work is energy, just different ways of calling it work. Work is what happens whenever something applies a force and is changing the energy of the object. All right. Beautiful. Beautiful, beautiful cheetah. Fix your eyes on that. That'll be the last you see of that. Unless you rewind the video, then it's forever enshrined on the glorious YouTubes, the glorious interwebs. All right, we got the example 2 is find the work required to accelerate 1610 kilogram Tesla from 10 meters per second to 20 meters per second. All right, so we've got our little car. It's sleek looking. I don't know. Did you see the futuristic Tesla? like the truck, like real weird looking, but it has a mass of 1,610 kilograms. It's lighter. There's no big hunky engine in the middle. It's just vroom, just goes vroom vroom. The initial equals 10 meters per second. And then later on, it's moving at twice that speed of 20 meters per second. And we want to find the work required. How much work did our engine do? So here we can look at and use our Kinetic Energy Theorem to solve this. And it might be obvious, not obvious right away, to use this equation, but if you remember what does this change in kinetic energy mean? Well, it means final minus initial kinetic energy, which means 1/2 m v final squared minus 1/2 m v initial squared. And so we can, okay, I have mass, I have v final, I have v initial, so I can plug all this in and solve. So we've got 1/2 times 1610, and then we have v final squared, and then I have 1/2 1610, and then I have 10 squared. Now you could keep the 1/2 m outside and just do v final squared minus v initial squared first, then multiply it through, or you can do it in two terms like this. It's typically just written like this just because it's final minus initial, so you can see each kinetic energy component by itself, but you certainly don't have to write it that way. Yeah, so plugging all this in, you get a final work value of 241,500 joules of work that was done in order to double the velocity of our car. Now notice that work doesn't give us a time. We don't need to worry about how fast we did this in. And this is really a show of what energy represents. We're not timing this and saying, okay, the car went from 10 to 20 meters per second in 3 seconds. We're gonna get to that. That's something we call power. How fast something happens. Power is how much energy is changed per second, or the work done per second. In this case, we just want to know how much work would be required of our engine. If this happens over the course of a minute, going from 10 meters per second to 20 meters per second, is not very fast acceleration, but it's still going to be doing the same amount of work. And so this is something to think about, like the amount of work isn't dependent on how fast the energy changes. It's just on how much the energy changes by. Okay, so that's something to think about as you work through these ones. All right. Number 3, a 10 kilogram box is placed on a frictionless surface and a 10 Newton force is applied to the box. The box moves a total of 20 meters on the ice. How fast is the box moving after 20 meters? So let's draw a little picture. We got our, oh man, that is a weird color. That's some funky ice. All right, so let's do this. There's my magical ice. It's like straight out of Disney right there. We give it a little push. And the box slides. So 10 newtons of force. Maybe I'm not sure how someone could push this if they're standing on this ice like so, and they try and push the box. If it's frictionless, they're just gonna fall. So maybe they tie a string to it, and then maybe like this guy's like, I don't know how to push because my feet are just gonna slip out, and then I'm gonna fall to the ground. So maybe he like gets a buddy over here to maybe like lasso it with a rope. That's a cowboy hat. That's terrible. Let's square that up. There we go. Now he's looking like a cowboy. And then this guy maybe has like a little lasso that and so then he like flings it around the box, and then he's applying a force this way. Maybe that's what's happening. We only know that a 10 Newton force is applied. That's all the physicists care about. But I like to ask the difficult questions here. All right. A 10 kilogram box is placed on frictionless surface and a 10 Newton force is applied to the box. How? Maybe by a cowboy, maybe Indiana Jones. I don't know. The box moves a total of 20 meters on the ice. How fast is the box moving after 20 meters? So we grip this thing, we pull it a total of 20 meters. I wrote delta x there, but we've also written this as d, interchangeable here. The force and the displacement vectors are in the same direction, so theta is 0. And this might look familiar from our force times distance cosine theta equation in order to figure out the work. But how does that tie into what we want to solve for, which is how fast the box is moving? So after it gets to here, you know, how fast is it moving? It started at rest. It started at a velocity of 0. And now this guy's got to watch out. He's like, oh my gosh, this box is coming out toward me. How fast is it coming toward me, though? What's V final? All right, so it's like when you're trying to move something and you're like pulling it towards you, and then all of a sudden it's like falling towards you, and you're like, I got to stop this thing, or I got to get out of the way. That's what's going through his head right now, like in shock, but he's happy as he's a cowboy. All right. So we've got a couple things here. I can't go directly into this work kinetic energy equation because I don't have what the work is. And I also don't really have this change in kinetic energy. I know that I want to find MV final. I can look at this piece of the equation and analyze this initially, and that's what we're going to do here. And so we can do KE final minus KE initial. And if I look at this in terms of work equals change in kinetic energy, well, I know that KE final is going to be our unknown that we don't really have a grasp on yet, because I don't know what V final is. But I do know that V initial was 0. So I know that I didn't have any initial kinetic energy. Initial energy. Now, what you have to remember is, well, the equations we practiced on Tuesday was this work equals force, distance, cosine theta. So this helps you out a little bit. This is my left-hand side of the equation. And I'm going to go ahead and set this equal to 1/2 times 10 times V final squared. I'm going to plug in force of 10 newtons. I'm going to plug in distance of 20. I'm going to plug in cosine of theta, 5V final squared. And then I'm going to go ahead and cancel this out. So this becomes 40 cosine theta. This is 1 here. Divide the 5 over. So that gives me 40 equals V final squared. Which means I get a V final of square root of 40. 6.32 meters per second. All right. So it's a couple step process here. We had to start with this work equals force distance in order to calculate the work here. You could actually have calculated the work by itself as 40 joules and then plug that into this original equation. So you can kind of break this down however you want, but don't feel like you need to do it in a certain order. So number 4. While driving your car, you have to suddenly slam on your brakes, causing you to skid to rest. If you were initially moving 18 meters per second and the coefficient of friction between your car's tire and the road is 0.65, how far will you travel before coming to rest? Great question. Sometimes this happens. We're in our car here. I love my hat cars. And then suddenly, the person in front of us maybe pulls out, or, we are not quite paying as much attention as we need to be paying attention, or whatever happens, and we have to slam on our brakes. we have an initial velocity of 18 meters per second, and we know we can get a coefficient of friction of 0.65. What we want to know is how far did we travel during this time before coming to a rest. And so we've done actually problems like this using kinematics, where we calculate the acceleration, we use F equals ma, and it's sort of a similar process what we're doing here, but we're going to do it in terms of the work. So I can actually see, okay, I can see I can get the work here by doing changing kinetic energy because I have V final and V initial. Now I don't have mass here. The mass is unknown, but this is okay. If the mass is unknown, it's fine. You just have to keep that as a variable m, and you'll see it cancels out. It goes away. We actually don't even need it. So again, we're going to start with our changing kinetic energy equation, Ke final minus Ke initial. And then in the left-hand side, I'm going to do the same thing I did last time, which was plug in F distance cosine theta. Now, in this case, what is the force that I'm talking about? Well, you're slamming on the brakes of your car. There's friction. So the force of friction, which is going to be combined between the tires and the road and your engine, the axles and your brake pads, which are going to help you slide or come to rest without skidding. So all that is lumped into this one friction force. So there's a little bit more than just your car tires that are helping you to slow down here. Obviously, your brake pads have a certain coefficient of friction as well, but we're going to assume everything is in terms of this tire with the road. There has to be a stopping point, contact point, and it happens here, right? The internal friction here can slow the rotation of your tires, but they still need to be able to slow against the road itself. So that's what we're going to be looking at. This force of friction we have as mu Fn, which we've done before. And what is normal force? Well, normal force equals force gravity. So force friction, distance is unknown, and the distance is going to the right, friction is going to the left. So I'm going to get a cosine of 180 degrees. Ke final is going to be 0 because my initial velocity was 0. Or sorry, my final velocity is 0 right here. And my initial velocity will be 1/2 m and then 18 squared. So I have this m term here. I have d, which I'm solving for, and then I have this friction, which I'm going to plug in as right here as mu times the normal force. Well, if I draw my forces here, I've got the normal force and I've got gravity. And these two forces are going to be equal and opposite, which means that my mu Fn here is really going to be mu mg. And this is beautiful because it allows us to cancel with the m on that right-hand side. Since this term is 0, it's going away. Cosine of 180 is -1. So it's a little bit more complicated in terms of the math, but the negatives cancel. There's a negative on this side, negative on this side. We're multiplying, so these go away. And we're left with mu is 0.65 times 9.8 times our unknown distance equals 1/2 18 squared. And I can solve for distance, and I get an answer of 25.4 meters. And voila, we have it. And so that's how long it's going to take us to go to rest at that point in time. That's how much distance we're going to travel. All right. So these are 4 different problems, 4 different types of problems that you can solve when you're using this kinetic energy theorem. They kind of got a little bit more complicated as we went. We started really basic with this 1/2 mv squared. We plugged in and found final and initial kinetic energy subtracted to get work. And then we took that one step further, tying it back into our force distance cosine theta to solve 2 different problems, even going all the way back to our friction equation. So there's a lot going on here. So definitely review this. I'm going to give you guys a problem set tomorrow to try out. But until then, signing off here. So have a good day, guys.